Okay, so I will make a couple of announcements and then continue making circles and seeing what you're doing and making sure things are working well. So here is the list of subjects. So please give me, I'm going quickly, verbally address them, hoping that all of them have been addressed in the last time. But please attract my attention to any of the subjects that I need to cover again. So the propagation, we are working with a code that allows to predict future of a wave packet. This is a code that doesn't use standard approach of wave packet expansion. Instead, it uses the real space, Cartesian space, wave function as defined at the very beginning of the course. And it utilizes propagation of wave function with evolution operator. So why this choice has been made? Because the eigenstates, eigenfunctions are very specific for any specific system. And some of the systems, especially the chemistry of dissociation, do not have a good set of wave functions. And we want it to be universal. Later, as you'll see very soon, the code can be updated to any one-dimensional problem. The evolution operator includes Hamiltonian, and Hamiltonian includes kinetic energy, which includes momentum operator. So one needs to define momentum operator in real space. And it has been made with the literal definition through derivative, with some additional tricks that we do not care about, but it is higher order of finite differences. So, principles of wave packet propagation. One does set up an infinitesimal increment of time as a length of time evolution, and then apply time evolution operator for infinitesimal time to available wave function again. And at each cycle, at each step, one propagates it, one changes. The evolution operator changes wave function and sees what happens one step forward. Why don't we use second way without exponential, without evolution operator, just Hamiltonian times delta t? One can do it, but then error will be really huge. When we do evolution operator, it includes several orders of this term, I over h bar Hamiltonian times delta t in all possible powers, and the accumulation of errors is much smaller. The difference of three methods is that second and third use different implementation of momentum operator, different mathematical tricks to implement it. And the first method uses, defines both wave function and all operators in momentum space, propagates it in momentum space, but then converts the wave function and wave packet into real space with a Fourier transform. So when you see the method number 1 or method or any variable without label 2 and 2 or 3, it is related to definition of all operators and wave functions in momentum space. This has mostly academic interest, not much practical, because in chemistry-related problems, we need a real space. So then approach number 1 will be used only right now for academic purposes. Later in projects, we will neglect it. Okay. No one selected commutation, but I will nominate someone. You know that one of the basic properties of quantum operators is that if you write them in one order and another order, the result may be non-zero, and it is one of the challenges to curiosity. Check if our numerically defined operators will match these expectations. So whoever will do it, or I may do it for demonstration, just takes two operators, whatever, like position and momentum or something more advanced, multiplies in one order, subtract when they are multiplied in another order, and then visualize the matrix and sees what happens. So if it is position and momentum, then one should get identity matrix, which will have ones on main diagonal and zeros elsewhere. But if we fail something, or if the method has limitations, one may observe deviations from this expectation. In some sense, these two chapters duplicate each other. They're not unique, and I will try to work to merge them. So, when all operators are defined, and again, I'm addressing those things only verbally to save time and go to new things, because we went over these two chapters last time, right? If we are neglecting the eigenstates expansion, then our initial condition is defined literally as wave function in Cartesian space, which is convenient to select as Gaussian function because it corresponds to semi-localized electron somewhere in one region of the space. And then we have well-developed mathematical tools to set up, to define the average position, average width of this distribution. And we recently agreed, at least I was writing on the blackboard, if one multiplies Gaussian wave function times plane wave, it will mean traveling Gaussian wave function. So you define the average momentum, and then you let it move. So you set up initial velocity. Such initial velocity is needed, according to Braden, to any chemist. So what we started in class today in the morning, we will slowly go on the way to realize that not only electrons are quantized, but also the protons and all other atoms can be quantized. And if you are looking on to nuclear reactions, on collision of two atoms, then we need to set up initial momentum to them. And then representing an atom as Gaussian distribution with fixed momentum is not a bad idea. Make sense? Braden is not protesting. He's agreed. I'm picking you up just because you are sitting closer. So, initial condition is chosen as Gaussian distribution. Lagging mark. Alternative methods to compute quantum dynamics. Where volunteer is one. Alternative methods meaning ways to define momentum operator or going into momentum space instead of Cartesian space, and then projecting results onto Cartesian space just for convenience of the audience and for better visual representation. Next. Discrete representation of wave functions in space and time. This is probably the simplest question. I'm not sure that it is sufficient for one subject of presentation. It means just that instead of mathematical function, continuous mathematical function, we discretize it. So split both position and space on grid points and represent function as a set of values at different grid points. That's it. And if it is position and time, then it is two-dimensional grid space. Maybe we can merge it with something else. But what we can do today, if time will allow, we can take either wave function or probability distribution defined in this grid space at all points of time and visualize it at once. Instead of dynamics, you can visualize it by the same methods as you guys shown in the last presentations. Methods to visualize a matrix. So it is grid points. Numerical normalization of wave functions in discrete representation. If you define space through grid points, and you know the range of the wave wave function is defined, you also know that integration over this range of the wave function square should be normalized, should be 1. And this integration will include, as any integration, dx, the increment, the space, the distance between two grid points. So normalization constant will depend on the size of your increment. And the one who will present it should address the question how the normalization factor depends on size of dx, whether it will be square root of dx or 1 over square root of dx. It's also quite simple. Size of simulation cell versus time of simulation. This is the last thing we did a week ago, and when you were running the code today here, it is what you have observed, that the wave packet passes through the wall and comes through another side. So it is a signature of periodic boundary conditions. So if we prefer to avoid this strange effect of coming through walls and appearing, we just select duration of simulation shorter than size of the cell divided by momentum multiplied by mass, right? So if duration is chosen short enough, then you just not have this overcoming through the walls. But periodic boundary conditions are needed because otherwise the wave packet will reflect and interfere with itself much stronger. So it is a way to make this modeling more efficient. Also, if you want to, if you are modeling a plane electron in a free space, then periodic boundary conditions are much more realistic than strict boundaries with walls. Okay. Not here. Oh, now it is seen much better. So, suppose that we do have a tool, not suppose, we do have a tool that computes wave function at each point of time. And it is named as psi 2 psi, psi2, psi3, which is a one-dimensional array of values of wave function, and those values are complex. We already covered that we can take absolute value squared and plot the distribution. Or even if you didn't cover it, you can guess it through the visualization that you see. But now, if we have wave function at each point of time, we are able, or we should be able to compute any observable just by literal plug in the definition of expectation value into, how would you call it, direct product, Brian cat, row by column, definition of expectation value. A bridge that connects wave function to a real world. So I'm going to open the code, find the place where some of these observables are found, and then we will discuss one, maybe, then we will discuss it. So we are going to the code, and you already have a basic idea of the structure of the code. So one defines all operators, defines initial conditions, and then runs a loop over the time steps. And at each time step, the evolution operator is acting on the wave function. So for method 2 is g tau 2 is evolution operator acting on the wave function and updates the value of wave function. Now, how would we define the same thing for third method? Okay, so I'm focusing your attention on this line and then later on these two lines. And it may need some writing on the board. So this little segment of the board can be better than the big one. So if we need expectation value at given time, right? We put Brian cat and operator between them. But x, the position is very, so to say, trivial operator, and we do not care about complex conjugation. So just for simplicity, this is formulated as wave function absolute value squared times x dx. And you do see it where? You do see it in this, in my version of the code is line 117, but since I'm updating it very often, it may be a few lines off. So you see here, the summation is integration. X period is should be defined earlier as the either momentum operator or just array where values at each point of array, the value corresponds to position in real space. So we will need to scroll back and see where this x is defined. And prop 2 is a probability distribution. This integration skips dx because it is inserted into definition of wave function. So we, in order to avoid it here, we just define wave function in such way that it includes square root of dx, and then one can just replace integration by summation. So if you want to be meticulous, we need to go up and see what is x period before we do it, so that we do not jump too often up and down, forth and back. Let's look on the lines 122, 123. So here it is more literal implementation of the protocol to find expectation value. So you have wave function conjugate, and in case of a vector it is bra. Here there is operator of momentum that we discussed last time how to define, and here is the ket, the vector of wave function. And to make sure that it is normalized, one can put normalization integral up front and divide it. But it should work without it. We did set up initial condition in such a way that wave function should stay normalized. But just in case, numerical error may accumulate and additional effort to normalize is not a pain. So where are we going now? We are going to scroll up and find where x capital is defined, to be sure what we are doing. So, in some sense, x operator is not defined as an operator. It is just set of raising values. So we do define it as just array of increasing natural numbers from 1 to number of grid points. So endpoints is evidently number of grid points, and then multiply by dx, so that it will be dx, 2dx, 3dx, and thus, well, we shouldn't, I shouldn't speak, I should just open new figure and tell plot x capital, right? So about 200 points, but since dx is smaller than 1, it goes from 0 to 80. But this is done in a quick and simplified way. If we go for expectation value of momentum, it is more literal, more rigorous. So which variables so it is defined in line 22. Please stop me and ask questions if you think it is necessary. So now I would like to check numerically what is this average. I can just type and get some number, which would likely, so 34, which would likely correspond to average position of the wave fund, or wave packet, right? Make sense? Somewhere in between 30 and 40 in atomic units. So what is not comfortable for me and for you in this definition and in this literal portion of the program? that this is value of this is expectation value only at specific point of time. And right now, since our cycle over time is over, it is a value at last instant of time. But compared to class of problems that we did by pen and paper in the class and in the homework, we may want to follow the trajectory of expectation position of expectation value of position at each point of time, right? So as we run through the cycle, we may want to save the value of expectation value of position at each point of time, or accumulate it into a specific variable. Make sense? So to some sense, I'm jumping between subjects, but and you're very welcome to stop me and navigate into other direction. But I think it will be mostly beneficial if we right now we will look for variable that accumulates values of this expectation value of x at each point of time. Here it is, two lines below. So, in case, I'll better show an example. So, let's remember, we don't have variable a. If we define a simple vector, just explicitly, and then we can define another vector as memory, as recall of previous vector, which may have different lengths, and then one more element. Then this recording accumulates one more element and makes the length of the vector by 1 unit longer. So same idea is implemented here in line 119. So we define the array AVGS, which will make S for plural, for many averages. And then we accumulate there the value AVG at each point of time. So how do we check if it is truth, if it makes sense? We should plot AVGS, right? Which should contain trajectory of position expectation value.
Question is on
yes.
notator syntax. So you have bracket AVGS and then semicolon. Does that mean that it's vertical rather than horizontal addition?
Yes, it is. If it is
so
column.
Equally, I could hit enter.
Yes. Okay. How do you make this zigzag? Please try to do the same, and now we will discuss what does it mean. with this. Yeah. Let's run the whole details. Do you get it?
Oh.
Yes. Okay. Do you manage to install MATLAB on the laptop?
No, I don't have the license.
But anyone here at NDSU has license
Oh, okay.
by right of birth.
I could try to do that. Probably
Yeah.
crash the crap out of the laptop.
So that you can practice this fun at home, not waiting.
Right.
So, what is the interpretation of this line? Compared to, I don't remember literally, but I think it was problem number 3, no, 4, problem number 4 in homework that we collected today, and you were grading. What are the expectations for by the way, before I continue, we can immediately add the labels. So y label x of t in atomic units. So according to your homework assignment problem number 4, right? And according to Newton's law number 1, a particle in free space on which no one acts should move with constant velocity. Right? Agree? No one objects. Which is okay here. But why does it go down? How do you interpret? Why, according to Sir Isaac Newton, it should go here continuously. But then here in our simulation it drops down. What happens?
It interacts with the walls.
Well, not interacts. There are no walls. We have periodic boundary conditions. It just reappears from 0. And then, so it goes out through right wall and reappears from the left wall. Not wall, but border, boundary. Make sense? Why doesn't it does not literally touch the edges? Who's presenting this subject? Let me see. You cannot make everyone to be 100% focused, but expectation, values, position, and momentum. Aha, they're not here. So Luke and Jan. Luke and Jan, if you are watching, listen from here on. So, which question was I asking to myself? Why it never touches the wall? Well, we did set up the width, and when we are going through when the part of the wave packet disappears and reappears here, another part stays here. So it is very unphysical situation when a part of me has already made a step outside of the door, and another part of me is reappearing from here. So it's very non-physical. It is artifact of the method, which we can avoid by selecting shorter time of presentation. You may want to understand what is going on and avoid these artifacts in more scientifically important simulations. Make sense?
So could you like think of that like slope line going down as like an average of the total electron's position?
It's an average of half of my cell that already stepped out of the door and another half that has already reappeared. So here it shows that it is in the middle of the box, because like if you split me on two parts, my average position will be in between. It's not physical. You cannot trust the method here and there. Although after, you can trust it again. Okay? So what do you expect to see for momentum? Yes. Do we expect to see any discontinuity for momentum? Probably not. So even if I'm running through the box and reappearing, I do not lose the velocity. It's still same direction of motion, from right to the left, with the same pace. How do we check it? Let's look through the code and identify. So the expectation value of momentum is AP, but it is only for specific instant of time, right? If you want to analyze the trajectory, we need to accumulate it in the same way, right? So we may want to plot A, V, E, P capital and see how does it change with time. And by the way, if I want to keep old image, I can type hold on. And PVE P. Huh, nothing changed. Okay, hold off. What am I doing in the wrong way? They have so imaginary part of momentum is small, 10 to minus 16 is almost 0, and real part of momentum, okay, it is 6.9 and it doesn't change. Whoever told that it should be constant was correct. And here we do have several methods, so we should AVEP3. Let's check another AVEP3. By some reason it gives different value, but the conclusion that it doesn't change in time stays correct. And just in case, if you do not want to plot but want to check that it is a healthy array or healthy vector, we can do size, and then it tells what is the dimensionality. So it is 120 time steps. Any questions on this subject? If no, I'm curious to see what is the next subject. Accumulation of expectation values. Saving numerical data into files. Well, same as last time. If you have an array, you just let me see. Maybe it is already been saved. But if it is not, you just do save. Okay. Then it doesn't want to save complex numbers. Now I finally discovered that the last is file name, and pre-last is actual. No. It is not as simple as I expected. Okay. Okay. So I defined an array that contains only real part. And trying to save. Okay, it did work. Now I do ls to see which files are available here, and I have this almost a Raven, real part of AVP3. And where am I? PWD desktop. Desktop. Okay, well, it is very pathetic set of data because they are the same at each point, but it is a saved results of advanced quantum calculations. Well, maybe in the next steps we can save something more interesting. What is next? Saving numerical data. Computation of expectation values, position and momentum. Oh, we already did. Expectation values of energy and uncertainty. Energy a little later, but uncertainty right away. Why do we need uncertainty? By some reason, we spend so long time in the class focusing on the uncertainty again and again, and assigning some philosophical I'm slowly learning how to operate it. So the uncertainty is important philosophically, and it is important because it practically, what is the use of uncertainty? Just very, I wouldn't say cynically, very practically for this code and this kind of project. The uncertainty of position is the width of wave packet. If you want to split our effort on 2 evenings, first evening I run for 100 time steps, and next evening I run for another 100 steps. I may want to record what is my wave function and then reset it again. And the width, uncertainty is a width of the wave function that we use as initial condition. And from this point of view, we may, even if you forget about any philosophy, we can analyze whether the shape of wave function is changing and whether we can use outcome of the simulation as an input for next one. So if we already have the expectation value of position, how do we define uncertainty? Forget everything we did in class. Recall basic data analysis that you started your university career with.
Standard deviation.
Yes. Yes. Which is?
Squared average minus average.
I will use new color to make it more impressive. Right? So why we cannot use just x squared and then find expectation value? Basic, when I look on this equation, I see, okay, second power of x operator, take expectation value. Why do we need to subtract the expectation value of x operator itself?
Related to the mean spread.
Right, right. When we do have this Gaussian or nearly Gaussian wave packet, if we start measuring position from origin, and if you take the square of this one, it will be a really big number, independent on the width. But if you will start measuring distance from the center of distribution, then it will be real measure of the width parameter, right? So what we do practically, we just take the expectation value that has been already computed minus square and then plug it into procedure to compute expectation values. It's like expectation value of expectation value. So let's look into the code and identify this place. So I would look at the line 118. Basically, it's next line after finding the expectation value of position. Next is the standard deviation. So if you look on this line, so here is our position minus expectation value squared, and then we implement multiplying by this probability distribution and integrating, right? The sum stands for integration. Again, this is a little simplification more towards intuitive analysis by human brain. Because here x is just an array instead of two operator, and here we use distribution. Because even if you do it rigorously, the result will be the same. But for more momentum variance, for momentum uncertainty, we may want to implement the true definition of expectation values. So if you point your attention on line 125, you see here is expectation value of momentum at a given time minus operator of momentum squared, and then it is plugged inside a sandwich between bra and cat, right? So this ASP is what? Uncertainty of momentum. So ASP is uncertainty of momentum. I can add the comment, and this variance is uncertainty of position. Position. This one uncertainty of momentum. Save. So if I'm curious about these uncertainties, I may just plot variance. What? Am I doing right thing, or I'm doing something silly? I already know that I'm doing a stupid thing, but I will let you enjoy and realize it. What I'm going to get? If we found it only at one specific point of time, it will be just 1 point, right? Instead of we even do not see it. We do it with okay, just 1 point, so it's not interesting. So we need to, before analyzing at time t, we need to accumulate this data along the trajectory. And here, EVSP. P uncertainty as a trajectory period accumulated. So instead of ASP and variance, we need to AVESP. Make sense? So we need to look on the values of this uncertainty at each point of time, which has been made at each iteration by accumulating in this variable. Okay. So instead of variance, what do I do instead of variance? Oh, variances, plural. So how do you interpret it? Oh, let me walk around and see that you have plotted it. Otherwise, it will be I will be talking to myself. Turn around. No. So when we were playing with expectation value of position, we identified that there is something crazy going on at in the middle, well, maybe 2/3 from the beginning of the trajectory, right? when the wave packet passes through the boundaries, right? So we may expect that similar thing is happening for variance. So when wave packet passes through the boundaries, one half is approaching this wall, and one half is reappearing from another one. And by formal definition of variance, of uncertainty, it is very uncertain. It's either very far to the left or very far to the right. So the value of uncertainty should be comparable to the size of the box. Or if you define it this way, then will be compared to the size of the box squared. Therefore, we get this number of above 1,000, right? So if we carefully design the time duration of the simulation, we will not get into this strange effect, although we should understand of the limits. What if we do not have time to rerun? What if you have this data? What do we do as self-conscious, fair scientists? We just drop bad data. we will focus on the initial portion of the trajectory and forget about the rest, right? How do we do it in the quickest way? We click on the arrow, which means edit the image, and select the x-axis to run, let's say, to the 80 instead of 100. No, too few. 50. Too much. We need less. 25. So fair game. Now we focus only on the initial part of the trajectory, right? At the initial time, well, we start from 1, not from 0. We see that variance equals 2, which was our initial condition of the for wave packet. If you scroll up, you will see x var equals 2. It is our initial condition. And if you look on the initial shape of the probability distribution, you will see that it has the width equals 2. Then, as time passes by, how does it change?
Grows quadratically.
Grows quadratically. According to whom?
Heisenberg.
Yes. Heisenberg. Werner Heisenberg, from Germany.
Yeah.
Heisenberg uncertainty principle that tells that delta x times delta p is bigger or equals to h bar squared divided by something. So it was also one of your homeworks, where position and momentum uncertainty doesn't change in free space, but position uncertainty grows quadratically. Therefore, it will be always above the quantum limit. So this is reliable data. At a time before wave packet approaches the walls, and second limitation, before the edges of this popping up, expanding wave packet start touching the walls. So you see, when the width is reaching big value, like 20, it means 20 to the left, 20 to the right, it's always touching the walls, and then some aberrations will start. So probably we should select time not just length of, based not on the length of the box, but maybe length of the box divided by 2, to be sure that we are free of unphysical artifacts of the method. Make sense? What I'm missing? Uncertainty of momentum, which is saved in which variable? Let's look here. it is something like, yes, AVEP. Maybe AVP2. One of those. ASP. Okay, AVSP. Let's do it. Copy. Plot. Paste. So, what do we see here? Well, you shouldn't hesitate to say that you see garbage. And if you ever are selected to play a role of reviewer of scientific papers, you shouldn't hesitate to write it in your report. Like, an author generated a garbage data. Well, we still need to try to interpret and understand what is going on. So most likely, this variable or this trajectory of values of variable has real and imaginary part at each point of trajectory. So typically, x is real, y is imaginary. And imaginary part, see, it is 10 to the minus 12. We still can consider it as 0, right? And for the real part, you see the values. So 50.17, 50.17. So it is basically the same number. So it is a little numerical noise near the actual value of the uncertainty of momentum. So if we replot the same image as if you plot real part, we see that something is going on due to numerical effects, but basically it is very close to constant. If we change the range of values, the interval on y-axis, let's say from 40 to 60, then it will look as a very, very constant line. So we just playing fair game, right? From 40 to 60. And now we need to label it, and then we can conclude up to numerical precision with whatever shortcomings of the method, the uncertainty of momentum is constant, right? So it goes very well in according to Dr. Heisenberg. Product of them, of uncertainty of position and uncertainty of momentum, expands. And it is nothing wrong to see that one of them is constant while another one expanding. What is next? Expectation value of energy. Oh, this is the cool stuff. Austin is not here, right? Aaron, you are not Austin. Good. I'm learning your names slowly. Austin, look from here. It is for you. So, in regular life, Hem is a food. In the notations of this code, it is Hamiltonian. And we need to practice expectation value of Hamiltonian, right? So I shouldn't basically hesitate to type something like psi 2 apostrophe times hem 2 times psi 2. I may fail, but I didn't. So it is expectation value of Hamiltonian computed in a literal definition of expectation value. So we can choose our operator as Hamiltonian operator, and we put bra and cat on the left and right. We also can accumulate it and see the trajectory, but because of the law of conservation of energy, it is not expected to change. Right? And since we do not have potential energy, and so it's only kinetic, probably this value of 25 something should be very close to initial momentum squared with account of all this divide by 2 mass h bar squared, but the h bar is 1 in this system of units, atomic units, and mass of electron is also 1. So we probably can take initial value of momentum squared and divide by 2. Let's check if this hypothesis is correct. So I would go to the very beginning. Oh, see! Haha! P not equals 7 in atomic units. P naught squared will be 49. Divided by 2 will be very close to 25. It will be like 24.5. And the rest is either numerical error or quantum effects, because it is not classical but quantum particle. Right? How to check whether it is numerical error or quantum effect if this question challenges you as a scientist? You change variance, initial variance, and see how this result changes. If it stays the same, independent of variance, then it is numerical error. If it will grow as variance grows, then it is quantum effect. If you're curious, you will do it yourself. I wouldn't say that I'm not curious, but I'm super lazy and I want to go over the whole program today. Or maybe we should do it. No? What is X? Austin, you can relax now. Visualize real and imaginary parts of wave packet. So it's third choice of Mark and third choice of Jan. So if I just type plot psi2, what a wonder I get. So how do, let me check. So I have typed plot psi2. Let me go around and see if we have similar things or maybe something better and smarter. So everyone got this star. How do we interpret it? What does it mean? Is it numerical error or it is expected result? Any ideas? We were expecting to see Gaussian wave packet, right? At least we started with Gaussian wave packet and we ended with something that looks like Gaussian wave packet. Why are we getting star instead of continuous Mexican sombrero? We do have enough input information even if we came into this class and started doing it only today. We already had this effect.
It's plotting imaginary versus
Yes, yes. So wave function at each point of space has imaginary and real component. And since it accumulates phase, it quickly goes in from real to imaginary domain and makes circles there. So at each, if it is a complex number, then at each point of space, it is one of the rays of the star. So you cannot, therefore, for visualization, we use probability distribution. But if you are curious to see wave function, we need to plot real or imaginary parts separately. So type plot real. You see? Please try it. And I'm going to do just do this one.
Yes. Yes.
Can you show? Because some of us are playing with parameters and getting shapes. Okay. So, how do you interpret it? What does it mean? I will try to my best to avoid any exams. Maybe accept quick questions on presentations. But if you would have exam, it would be a perfect question for the exam. So interpretation of the structure of real and imaginary part of the wave function. So how does it correlate with what we were talking about at the very, very beginning of the course, maybe 1, 2, 3 first meetings? I'm not going to answer you. Instead, I'm going to do another numerical experiment. So save this image, maybe as by, how do you do it? By screenshot? Print screen. Or maybe just open another window. And then I'm going to modify the code by going into beginning of the here and setting up different initial momentum. So making it smaller speed. Save and run again. What's the name of the code? WP. So I did set up smaller momentum, smaller velocity. And now I'm opening new figure once again and repeating this exercise of plotting wave function. So let me repeat the question. How do we interpret? So there are two lines, red and blue, for real and imaginary components of the wave function as function of position. So what do we see? How do we interpret? From what we started at the beginning, we would expect sombrero, right? Gaussian function. And later, when we do to probability distribution, or before when we did probability distribution, indeed, you have seen these sombreros, right? What do you see here? So first, it has positive and negative parts. So both real and imaginary can be positive and negative. Second, if you close the eyes, drink some intoxication, and take the lights off, approximately you will see that here it will be the envelope function of this thing will be something like sombrero, something like Gaussian distribution. But the real and imaginary components of wave function demonstrate quick oscillations in space, right? So it is what you should answer an exam if you have an exam, if such question is posed to you. It can be not in this class, but in your future life, like in GRE, subject GRE, for example. If you're looking to scientific career and Harvard and so, like this. So, oscillations. What these oscillations depend on? What the frequency of these oscillations depend on? Again, it is, we went through this question in class 10 times. We never visualized it, but we verbalized it 10 times, I guarantee. So, oscillations of wave function, which can be denser fringes or sparser fringes. What they correspond to? Please develop your answer, even if you don't feel comfortable to do it out loud. Maybe write in your notebook or just think in your head how you interpret it. And now start answering if you are brave. Yes, closer. But there is an even more strict definition. Going literally with Bohr model, definition of plane waves, and concept of the only one operator that we need to memorize. For high, very close energy, but if the particle has large momentum, then wave function exhibits highly dense fringes, right? So this fringes is inverse of the wavelengths is inverse of momentum. High momentum, dense fringes. Low momentum, sparse fringes. If I set up, no, I will not tell it. I will just do it. So let's do another experiment. Set up initial momentum equals 0 and repeat this image.